All right, I just watched a video from Music Theory for Guitar user on YouTube, who I love, on generating. He had a standard lick, and he said, okay, you can do some operations to turn this one lick into 720 licks. And I thought this was a great example of combinatorial principles. And sometimes when combinatorics is not quite as easy as it looks. So basically what he did, he had a few different operations. I'll go ahead and use the same words he did. So sequencing gave him times 5, and then there was retrograde, which is times 2, and inverse, which is times 2, and then he had one he called phasing, which was times 6, and then he had one that he called expansion, which he actually wound up doing times 7, but I'm going to leave it times 6 to get the 720 that he got. And so we multiplied all these numbers together and got 720. So this is, of course, in combinatorics, this is called the multiplication principle. Multiplication rule, or it's also called the fundamental counting rule. But it doesn't always work. This only works when all of your actions are independent of each other, meaning that each action has no influence on the other. There's two ways this can fail to be independent. One is if your actions are noncommutative, meaning that the order of the actions matter, which indeed, that's the reason I sat down and do the calculation, because when I looked at the retrograde with the phasing, it's clearly that these two do not commute. So I wondered, well, maybe because of that, there's actually more than 720. But there's one other issue that can also happen besides being non-commutative. It could happen that there's some sequence of these. Well, I take that back. This only happens if it's non-commutative. But if it's non-commutative, there could be some sequence of these that actually doesn't do anything. You get redundancies. And that actually does happen. So because of this, instead of 720 licks, we're actually only going to get 360 licks in this particular case. Okay, so that's a real quick explanation. You might want to watch that video first. It's just a good video. I really liked it. But let me, real quick, for the non-math people, just explain why just show you that you don't get the full 720 licks. And for all the math people, then we'll explain how could you actually figure out that it really is exactly 360 licks. So how do you do a combinatorial problem like this where we have this non-commutative stuff going on? All right, well, let's do it. So just for all you non-math people to see that you really do have redundancies, let's take his original sequence, D, E, F, G, C, or sorry, E, C, D, which let me go ahead and write in the numbers as well. This is +1, +1, +1, -2, -2, +1. So in terms of the scale, I'm going up 1, up 1, up 1, down 2, down 2, up 1. Okay. So first thing we're going to do is we're going to do inversion and see what we get. If we do inversion, all our pluses become minuses. So -1 becomes C, -1 becomes B, -1 becomes A, +2 becomes C, +2 again becomes E, and then -1 becomes D. So that's inversion. And then retrograde is where we write the sequence backwards. So this is D, E, C, A, B, C, D. So this is +1, -2, -2, +1, +1, +1. So in math speak, we would call this RI. Actually, these commute, so it doesn't matter. But just the math convention is whatever you do first goes on the right, and then the other one. So this is inversion first, and then retrograde. All right. Well, if you look at this, you see this is basically the same sequence of numbers. I started out with 3 1s, 2 -2s, and then a 1. If I started here on the A, or sorry, no, on the B, I have 1 1 1 -2 -2 1. So in other words, let's do this guy. So if I start with the original, D, E, F, G, E, C, D. So first I'm going to do phase 2, so that means start on the F. So F, G, E, C, D. This D is the same as the D at the front. So the next thing is E, and then back to F. And now I'm going to shift down, or not shift, what did he call it? Sequence down by 2. So bump all the notes down by 2. So F becomes D, G becomes E, E becomes C, C becomes A, D becomes B, E becomes C, D becomes, or sorry, F becomes D. Notice those two are exactly the same sequence. So sure enough, if I take the original lick, if I do retrograde inversion retrograde to it, I get the same thing as if I phase twice and then sequence backwards by 2. So I have a redundancy here. And because of this redundancy, the 720 is actually doubled. It should only be 360. Okay. All right. So now for all you math people that want to know, how can I be sure there really is 360? And really what's all the structures going on here? Let's delve into that. Okay. So let's look one at a time at these operations he did. There was the sequencing, there was the inversion, retrograde, there was the phasing, and there was expansion. Actually, I haven't talked about expansion yet. Sequencing is not particularly interesting. This is just a action of Z7, or you could even think about it as Z if you want to think different octaves. But this guy, yeah, it's just changing what note you start on. So that's not very interesting. Inversion, so for the rest of it, I'm not actually going to look at these sequence of notes, because if I mod out by the sequencing, I can start on any note I want to. The important thing is this list of numbers right here. So I have 6 numbers, and by the virtue of the fact that the lick ends where it starts, really what I want is 6 numbers that if I add them up, 4, 5, 6, I get 1. So I'm, or sorry, not 1, 0, because I have to, this is because I end where I start. So I can think of this as just being a single vector, right? Okay, well, what did inversion do? Inversion, it changed the sign on all my, so my +1s became -1s, my -2s became +2s, so forth. So mathematically, what's going on with inversion is your vector is just getting a minus sign. That's no big deal. Let me skip retro and phasing for a second. Expansion, which he does at the end, is actually your vector just gets multiplied by a positive integer. So if I put these two together, I just have a goes to n times a, where n is a non-zero integer. So again, kind of like sequencing. So we've got this addition by elements of Z7 or maybe Z. That's pretty simple. Likewise, these two together can be just thought of as a multiplication by a non-zero integer. So that's pretty simple. The more interesting thing is what's happening with this retro and with this phasing. So the phasing was changing our starting point. This is a cyclic permutation. And this retro, well, retro by itself is a little weird, but if I go up here and look at the retro inversion, so here's the original sequence. This one is the retro inversion. So let me write those down again. You can see what's going on. So the original sequence was 1, 1, 1, minus 2, minus 2, 1. The retro inversion was 1, minus 2, minus 2, 1, 1, 1. So we see this is just writing the sequence backwards. So if I do the retro inversion together, it's just writing the sequence backwards. So mathematically, this is a little easier because it's just a permutation, whereas retro by itself not only has the permutation, it also has the sign change. So just to make life easier, we're going to work with this retro inversion instead of just retro. Okay. Well, these permutations aren't just random permutations. If you stare at it, this looks very geometric. So I'm going to put these on a hexagon, and we'll see geometrically what's happening. So I'll put my original sequence here, or you could put any sequence there. So you see what phasing is doing. Phasing kicks the first number to the back, right? So, by the way, I have a distinguished starting point on this hexagon. So let me just put it at the top because that's where I put it. So if I kick this first number to the back, that means that this first one should go right there, right? So phasing turns into a 60-degree rotation. What about this retrograde inversion? Well, you may have to stare at it for a second, but if I put the Ri on another hexagon, so this is the Ri hexagon. One minus two, 1. You can see that Ri is actually reflection about that dashed line. So, okay. And I mean, this is, of course, I just labeled it with the sequence from his video, but you could put any sequences here you can check. Phasing is always a 60-degree rotation. Your retrograde inversion is always a reflection about that diagonal axis there. Okay. So now we have the question, well, is this commutative? And of course, the answer is no, because we know that the dihedral, so this rotation reflection, they generate the dihedral group of on a hexagon. So, and so the first question is, do we get actually more than 12? I mean, this there's 6 rotations and 2 reflections. I mean, this guy has order 6, this guy has order 2. I mean, if you have a general group that's generated by 2 elements, and one has order 6, one has order 2, what's the order? And the answer is it could be freaking huge. You don't know. I mean, it could be infinite for all that goes. But we know that the dihedral group actually does only have order 12. So our first question is answered. We do have not more than 720 licks. And likewise, for a generic lick, we would get the 720 licks, just like the way music theory for guitar said. But this is not a generic lick, this is a specific lick. So is there a chance of redundancy? And of course, we already know the answer is yes, because we saw it at the beginning, but how did we figure that out? Well, we do it by seeing, is there anything in the stabilizer of this group action? Where stabilizer means, is there any particular symmetry of the hexagon that leaves all of our labels invariant? And sure enough, you can see if I reflect about the other diagonal, that reflection, I mean, it's the symmetry of the hexagon, and it also leaves all of my labels the same as they are. So because of this reflection right here, this is going to give us a redundancy. And we can figure out what that redundancy is just by writing that reflection in terms of our 2 generators, P and Ri. So I have to think, how do I write this reflection in terms of the retrograde inverse reflection and a rotation? Well, all the reflections in the dihedral group are just differ by rotation. So I can just do my Ri first and then see how much I have to rotate it to get where I start to get the one I want. So let's do that real quick. Let me put the numbers 1 through 6 on here so it's easier to see what's going on. 1, 2, 3, 4, 5, 6. So if I do my Ri guy, I get, so Ri is reflection that way. So 1, 6, 2, 5, 3, and 4. As opposed to if I do the one that I guess I'll call him stab because he's the stabilizer. The stabilizer is reflection about that one. So it would be 1, 2, 3, 6, 4, 5. And so I just need to stare. If I took my stabilizer and rotated it twice, I would get my Ri. So if I do retrograde inverse, that's the same thing as if I do my stabilizer one first and then rotate twice. So, and then of course the point is the stabilizer one, when acting on this particular lick, so for that particular lick, the stabilizer doesn't do anything. So for as long as I'm just acting on this one lick, doing 2 phases is going to be the same thing as doing a retrograde inverse. And of course, when we originally did this, we had a sequence by 2, and that's because we kind of threw that out. I mean, so the phasing actually changes the starting note. So really, SP is really the cyclic permutation. But anyway, I'm not gonna, that's just changing the starting note. Anyway, that's how that's how I knew this particular combination would wind up giving the same thing. It's not like I sat down and wrote down all 720 to see if there was any redundancies. I drew this hexagon and said, oh, this hexagon has a symmetry line that's not being accounted for, so that's going to give us a redundancy. And this is how you work out, back in terms of the original music theory, what is that redundancy. So anyway, hopefully you enjoyed that. I like combinatorics problems, and this seemed like a fun one, so hope you liked it.